Hello everyone, my name is Saubhik Maulik, Assistant Professor of Department of Electrical Engineering, Haldia Institute of Technology, Haldia. So we are discussing on the topic of power factor correction by interleaved boost converter. Already it is discussed that why power factor correction is required for AC to DC converter fed loads. Because in case of rectifiers, the output voltage that we get is in the form of pulsating DC. Now to make that rectified DC voltage constant, we use capacitive filters. The introduction of capacitor distorts the input current because the current drawn will be in the form of spikes, and the power factor as well as the THD gets deteriorated. So that is why we use, after rectification from AC to DC, we use one converter, DC to DC converter, and the current drawn by that converter is controlled to make the input current same as the input voltage, having the same sinusoidal shape. Now among different DC to DC converters, boost converter draws continuous current. That is why boost converter is most suited for the purpose of power factor correction. Also we'll discuss about the interleaved boost converter in this video. So boost converter, already it is discussed that single phase AC supply voltage through rectifier is converted to a rectified pulsating DC output, which is V in. It is fed as the input of the boost chopper or boost converter. The boost converter consists of inductor, switch, diode, and obviously at the output there is load. The capacitor is used to make the output voltage constant. Generally in choppers, MOSFET and IGBTs are used as switch because chopper switching frequency is very high. To keep that switching so as the switching frequency high, we need to use a switch which has a low switching loss. Both MOSFET and IGBT has low switching loss. That is why MOSFET or IGBTs are used in chopper. So here also in boost converter, as we can see that there is inductor L, switch S, diode D5, capacitor, and the load resistance R. Now inductor current IL will flow through inductor L and then switch S if the switch is on. If the switch is off, IL will flow through inductor L, diode D5, then the load and back. So irrespective of switch is on or off, the IL will be flowing. When switch is on, then also IL will flow. When switch is off, then also IL will flow. Now this inductor current IL will be made to follow a certain reference waveform which is rectified, which is the reference waveform for the current will be similar to the rectified DC output voltage, which has the ripples in it. So if the output voltage and the current IL has the same shape, then also the input voltage and input current will have the same shape. One more thing here to discuss, that inductor current IL, when switch is on, at that time inductor current IL will increase because inductor will store energy. When switch is off, inductor will dissipate its stored energy, it will change its polarity, so IL will decrease. So when S is on, IL will increase, when S is off, IL will decrease. So as already discussed, average current control technique will be used. First, as I said, the reference signal will be generated, which will be in the form of the shape of the reference current will be the shape of rectified DC output voltage, as it is shown by the current dotted line I average. The inductor current will be made to follow this average I average. So as we can see that when inductor current increases a little beyond that reference I average, the switch will be made off so that inductor current decrease. Again, after a certain time, when it falls below the average within a certain range, the again switch will be on so that current increases. In this way, current will increase and then decrease, increase and then decrease, but the reference wave, the average of this current will be same as the reference, that is I average. As we can see here, the current will follow the average, the inductor current IL will follow the reference sinusoidal form of reference current, which is I average. That inductor current IL will have some ripples. That means as current is increasing and decreasing, it has some ripples. But the average of it is proper sinusoidal. So if we can make inductor current IL to follow this reference, the power factor obviously will be improved as the average is properly sinusoidal. So the input voltage and input current will be in sinusoidal in nature and within the same phase. So the power factor will be improved, and obviously in this type of waveforms the THD also will improve, because it is no more the spike of a current, it has ripples but the average is sinusoidal. Now this is how we can make the current to follow the reference signal. First, the output voltage is sensed by a sensor, so V0 will be sensed and a reference voltage will be given as per the requirement. So the difference between the reference voltage Vref and the output voltage V0 is the error voltage. That error signal will be fed to a controller. That controller can be any controller, PI controller, PID controller, PASI controller, it can be any controller. That controller will generate an actuating signal. That signal will be multiplied by V in by K. What is V in? V in is the rectified DC voltage, as it is discussed in the previous figures, that the rectified DC pulsating DC voltage will be divided by a factor K, so that the current reference, which will also be in the form of sinusoid, is generated, rectified sinusoid. In that form the current reference also will be generated. So to create that, the input voltage, that means the rectified DC voltage which is fed as the input of the chopper, that will be multiplied by a factor 1 by K. So that will be multiplied by the actuating signal from the controller, which is voltage controller, so that the reference signal Iref can be generated. This Iref will be same as the I average that is discussed in the previous slide. It will have a sinusoidal type of shape but rectified. So that Iref will be compared with the inductor current L. Inductor current L is continuously drawn current. So IL and IREF will be compared and an error signal of current I error will be generated. That will be fed to again controller. Again it can be any controller. Then through that controller, compare the output of that controller will be compared with a comparator to generate the pulses which will be fed to the switch. If it is MOSFET or IGBT, to the gate of the switch, this pulse will be given. So this is the process. If we have to increase the reference voltage, we will increase the reference voltage accordingly. The reference current IREF will be increased, and accordingly the current controller will generate a signal through the comparator and the pulse width will be larger, so the voltage will be more, and vice versa. If we have to reduce the voltage, then also we have to follow the same process. We will reduce V reference, the pulse width generated will be reduced. So in this way, the continuous current drawn by the inductor will be made to follow the reference signal, which is varying sinusoidally but in a rectified form. There is no negative half cycle there, only the positive half cycles. So rectified DC voltages, which is pulsating DC, is taken, dividing it by a factor k. So pulsating DC into 1 by k, then it is multiplied by the voltage controller output signal to generate that pulsating DC pulsating DC sinusoidal reference current IR, that is compared with the inductor current IL, and the error signal is generated. So this is the process. Now, as it is discussed, if we follow this process, then power factor will improve by a lot, because now the input current also will follow a sinusoidal pattern. The only or slight problem is that the inductor current has ripples, small ripples, because when the switch is on, inductor current will increase. When the switch is off, inductor current will decrease. So there are ripples in the inductor current, as well as that same ripples will be there in the input current. So if we have to eliminate those ripples, then we will use interleaved boost converter. So this is the interleaved boost converter. In this interleaved boost converter, two boost converters are in parallel. The first boost converter, as it can be seen, that inductor L1 is there, which is connected with switch S1. There is diode D5 and there is load obviously in the output side. Similarly, for boost converter 2, there are inductor L2, then which is connected with switch S2. There is diode D6 and obviously the load. Now, what is the advantage of connecting two choppers or two boost converters in parallel? It is the control. So the inductor current IL1 and for the boost converter 1 and inductor current IL2 of the boost converter 2 will be controlled in such a way that when inductor current IL1 will increase, IL2 will decrease, and similarly when IL2 will increase, IL1 will decrease. How it can be ensured? The two switches S1 and S2 for two converters will be given pulse width, and those pulse width will be 180° out of phase. That means when switch S1 will be on, S2 will be off. When switch S2 will be on, S1 will be off. So suppose when switch S1 is on, the current IL1 will flow through inductor L1, switch S1 and back. At that time S2 will be off, so IL2 will flow through inductor L2, diode D6 and load, then back. So inductor current IL1 in this time is increasing and IL2 is decreasing. On the other hand, when switch S2 will be on and S1 will be off, at that time IL2 will flow through L2 and switch S2 then back, and IL1 will flow through inductor L1, diode D5 and load. So at that time IL2 is increasing, IL1 is decreasing. So the sum of IL1 and IL2 always give a constant current. In this way, the ripples in the inductor current and in that process in the input current can be reduced. So that will hugely improve the total harmonic distortion. The harmonics can be totally eliminated by giving the pulse width to the switches S1 and S2, which is 180° out of phase. So this is the advantage of interleaved boost converter. So that is shown in this slide. So as we can, so the IL1 and IL2 is shown, that how IL1 and IL2 can be made 180° out of phase, and their sum IL1 plus IL2 will be constant. When IL1 is increasing, IL2 is decreasing, and vice versa. So this is the advantage of using interleaved boost converter. In the conclusion, we can say that by using interleaved boost converter, the power factor as well as the total harmonic distortion has been improved tremendously, because now the inductor current will follow a sinusoidal pattern, rectified sinusoidal pattern, and in that process the input current also will follow a rectified uh, in the input current also will follow a sinusoidal pattern, which is same as the voltage. So the voltage and current will be in same phase, and as it is in same phase, the power factor will be close to unity. And the and especially by using interleaved boost converter, the total harmonic distortion is reduced, because obviously by using boost converter we are reducing the harmonic by making the current, earlier the current was in the form of spike, it was distorted. Now the current, average current is sinusoidal, but actual IL, after using only boost converter, the actual IL had some ripples. That ripples also can be eliminated by using the interleaved boost converter, where two boost converters are in parallel and the switches are triggered with 180° out of phase pulse width. So when one current is increasing, the other is decreasing, and their sum is a constant one. So that is why the total harmonic distortion will get improved, and the harmonics will be totally eliminated. So this is the advantages. In place of two boost converters in parallel, there are literature where three converters are also used in parallel, where the switches that will be used S1, S2 and S3 will be 120° out of phase. So, but that has a little more advantage than this one, but that is also becomes costly for using three at a time. So interleaved boost converters with two converters in parallel are very popular. So that is discussed here. So thank you everyone.